63 light-years away, there is a planet that looks from a distance exactly like Earth. Same shade of blue. The specific blue that on this planet means ocean, means breathable air, means somewhere you could stand and look up. On the planet you are about to visit, none of that is true, and the ways it is not true are worth sitting with. This is HD 189,733b. Discovered in 2005 through the same method used to find most of the first confirmed worlds beyond our solar system. Astronomers watched its star wobble, tugged by the gravity of something they could not yet see directly. What they eventually confirmed was a gas giant a little larger than Jupiter, orbiting its star in about 2¼ days, at a distance of roughly 1/30th of what separates Earth from the Sun. That close, the planet is locked in place the way a moon is locked to a planet. One side always faces the star, the other side is always dark. There is no sunrise here, and there never will be. The star it orbits is smaller and cooler than our Sun. An orange dwarf astronomers classify as type K. That detail matters less for the planet's temperature, which is dictated far more by distance. Even a modest, unremarkable star is bright enough at close range to build everything you are about to hear. Tidal locking is not a minor detail in this story. It means the entire imbalance of the system falls on the atmosphere to resolve. The day side receives a constant, unrelenting stream of starlight forever. The night side receives none forever. On a planet that spins the way Earth does, that imbalance resets every 24 hours. Here, it never resets. The only way this planet's atmosphere can survive that permanent inequality is to physically carry heat, at whatever speed the physics allows, from the side that is always burning to the side that is always dark. Keep that fact in mind. It is the underlying reason for almost everything else in this episode. When this planet was confirmed in 2005, the modern search for planets around sun-like stars was barely a decade old. Every method available at the time could only infer a planet's existence indirectly, through a star's wobble or a fractional dimming during transit. Nobody could yet ask what a planet like this actually looked like, let alone what its air might smell like. The instruments required for those questions did not exist yet. For years afterward, HD 189,733b was known mostly as an unusually well-placed target. It transits directly in front of its star from our vantage point, and that star is bright and close enough that starlight filtering through the planet's atmosphere produces an unusually clean signal. Astronomers sometimes treat a planet like this as a natural laboratory, a thin curtain of atmosphere backlit by starlight crossing in front of a telescope on a fixed 2-day schedule. That is a large part of why this single, ordinary-looking gas giant has been visited by so many different instruments across so many years, instead of being observed once and set aside. Then, in July 2013, using the Hubble Space Telescope, astronomers did something that had never been done for any planet beyond this solar system. They determined its actual color. Here is how NASA described the result. If seen directly, this planet would look like a deep blue dot, reminiscent of Earth's color as seen from space. Reminiscent, not identical. The color comes from a completely different mechanism. On Earth, blue means water, sunlight scattering off oceans that cover most of the surface. On HD 189,733b, there's no ocean. The color comes from what NASA calls a hazy, blowtorched atmosphere containing high clouds laced with silicate particles. Silicate is the basic chemistry of glass and sand. In the upper atmosphere of this planet at extreme temperature, silicate does not stay a solid mineral. It hangs suspended as fine particles, and those particles scatter blue light the same way water does on Earth, by coincidence, producing an identical-looking color for a completely different reason. The temperature involved is not incidental. ESA's own description of the finding puts the atmosphere at over 1,000 degrees Celsius, nearly 2,000 degrees Fahrenheit. The silicate particles responsible for the color condense out of the surrounding gas only at temperatures above 1,300 degrees Celsius. Everything about this planet's signature color depends on conditions closer to a blast furnace than to any weather system on Earth. This is where the glass enters the story properly. NASA's own current description is carefully hedged. It possibly rains glass sideways. ESA's original 2013 announcement was more direct. It rains glass sideways and howling winds. Both versions agree on the direction, and the direction is the strange part. Rain, everywhere you have ever experienced it, falls down. On HD 189,733b, whatever condenses out of that silicate haze does not fall toward any surface. It travels sideways, carried horizontally by wind faster than anything ever measured in any storm on Earth. How much faster took 2 more years and a different telescope to pin down with any real precision. In 2015, Tom Louden, an astronomer at the University of Warwick, working with his colleague Peter Wheatley, pointed the HARPS instrument, mounted in La Silla, Chile, directly at this problem. Their method was specific: high-resolution spectroscopy of the sodium absorption feature in the planet's atmosphere, tracking exactly how that signature shifted as the planet transited its star. A Doppler shift in one chemical signature, precise enough to extract an actual wind speed from a planet 63 light-years away. What they found: a strong wind moving at more than 5,400 miles per hour, blowing from the dayside directly toward the night side. That works out to roughly 7 times the speed of sound. Not a gust. A sustained, planet-wide current, day to night without interruption, for as long as anyone has been able to keep measuring it. For comparison, look no further than our own solar system. NASA describes Neptune as our solar system's windiest world, with winds that whip frozen methane clouds at speeds of more than 1,200 miles per hour, 3 times stronger than Jupiter's winds and 9 times stronger than Earth's. Neptune's winds are already the fastest anything gets among the 8 planets you grew up learning about. HD 189,733b's winds run at roughly 4 times that speed, on a planet sitting at a small fraction of the distance Neptune keeps from the Sun. Every account of HD 189,733b published since keeps landing on some version of that same number. Winds on the order of 5,000 miles per hour, strong enough that the word sideways stops sounding like an exaggeration and starts sounding like the only accurate direction. It had one more discovery left to give, and it came from the newest instrument capable of asking the question. In July 2024, an astrophysicist at Johns Hopkins University named Guangwei Fu led a team using the James Webb Space Telescope to analyze the same atmosphere in far greater chemical detail than any earlier telescope allowed. What they found, published in the journal Nature, was trace amounts of hydrogen sulfide in the planet's atmosphere, the same compound responsible for the smell of rotten eggs. This was on a world already documented at scorching temperatures around 1,700 degrees Fahrenheit, still raining glass that blows sideways on winds of 5,000 miles per hour. Consider what that means layered together. A planet you can point a telescope at and confirm is blue. Blue for a reason that has nothing to do with water, hot enough to keep glass suspended as airborne grains, windy enough to carry those grains sideways at several thousand miles per hour in one direction permanently because one side never sees day and the other never sees night. And now, on top of all of that, an atmosphere that and surviving long enough to describe it, unmistakably foul. None of this came from a single instrument or a single team. The color came from Hubble in 2013. The wind speed came from ground-based spectroscopy in Chile in 2015. The chemistry came from Webb in 2024. 3 separate results, 3 separate tools, more than a decade apart, all describing the same 63 light-year distant point of light, and all of them agreeing with each other instead of contradicting. That agreement is the real headline here, more than any single number in this episode. This is one of the closest, most heavily studied planets ever confirmed beyond our own solar system. Every new instrument pointed at it has added detail without overturning what came before. The blue is still blue. The wind is still roughly the same ferocious speed it was in 2015. And now we also know, with a precision nobody had in 2005, exactly what that wind smells like. Scale that outward for a moment. This is one confirmed planet in a galaxy holding an enormous number of stars, only a small fraction of which have been meaningfully surveyed for planets at all. Nobody went looking for the single most extreme example available. Astronomers studied the one closest to us, simply because read cleanly. If proximity and convenience alone produced a planet this violent, that says something about what a genuinely complete survey of the galaxy might eventually turn up. We are still near the very beginning of being able to run that survey properly. Here is the honest question for the comments. This is one of the best studied, most nearby exoplanets we have. It has been examined by 3 generations of instruments across nearly 20 years, and every single result has made it less survivable, not more. If our best documented neighbor looks like this, what does that suggest about the planets we have not been able to study nearly as closely yet? And does that make you more curious or less about what current telescopes are pointed at right now? We spent this episode on a planet you could recognize from orbit before you understood what you were actually looking at. There are worlds where recognition would not help you at all, where the ground itself is liquid, and where the first second standing on the surface would also be the last one your body ever experienced. That is next.